Whether you're carrying out an experiment in a school laboratory or manufacturing thousands of tons of chemicals in industry, one thing always matters: using exactly the right amount of each chemical. Too little and the reaction will not finish. Too much and valuable materials are wasted. To calculate those quantities, we first need to know the mass of the compounds we're working with. But there's the problem. Atoms are unimaginably small. A single carbon atom has a mass of around 1.99 times 10 to the minus 23 kilograms. Now, that's a perfectly valid scientific measurement, but it's far too awkward a number to use in everyday chemical calculations. Fortunately, chemists realized something rather clever. They didn't need to know the real mass of an atom. All they needed to know was how heavy one type of atom was compared with another. And that single idea transformed chemistry. Throughout the 19th century, scientists carefully measured the masses of different elements relative to each other, beginning with John Dalton's first atomic theory, and then continuing throughout the 19th century with the work of chemists across Europe. Increasingly accurate comparisons between the elements were produced. And then, in 1869, Dmitri Mendeleev organized those elements in terms of their relative weights and chemical properties into what would eventually become the modern periodic table. But when it came to those relative masses, there was still one important question to be answered. Relative to what? Every measurement needs a standard, a point to which all other measurements can be compared. Hydrogen seems the obvious choice. It is, after all, the lightest element, and it has only one proton in its nucleus. But hydrogen is a gas, and it is highly reactive. It's also surprisingly difficult to measure with great precision. Oxygen was considered too, and found wanting for similar reasons. Eventually, chemists settled on something much more practical: carbon, or more specifically, the isotope carbon-12. It was abundant, stable, and easy to work with. So, in 1961, the scientific community agreed that carbon-12 would be assigned a relative atomic mass of exactly 12, and every other atomic mass would simply be measured relative to 1/12 of that value. And that's exactly what we still do today. So, when you look at the periodic table, those mass numbers aren't actual masses of the atoms. They are relative atomic masses compared to 1/12 of the mass of an atom of carbon-12. If you're studying GCSE Chemistry, you've probably noticed that most of the numbers are integers. Carbon is 12, oxygen 16, magnesium 24, and it almost looks as though relative atomic masses are always exact whole numbers. In reality, they aren't. If we look at the more detailed periodic tables, such as those used at A-level or in universities, almost every element's relative mass is reported with decimal places. And there are three reasons for this. First, most elements exist as a mixture of different isotopes, so the value shown is an average mass. Secondly, protons and neutrons aren't exactly 1 unit each, and there's tiny changes in mass that occur when they're bound together inside the nucleus. And finally, electrons also contribute a very small amount of mass. The relative atomic mass of an element is therefore defined like this. It is the weighted average mass of all naturally occurring stable isotopes of that element compared to exactly 1/12 of the mass of an atom of carbon-12. And at GCSE, these values are simply rounded to the nearest half unit, making calculations much quicker while still being accurate enough for the course. So just bear that in mind as we move on. Now that we've got the relative masses for all of the elements in the periodic table, we want to use them to calculate the mass of our chemical substances, what we call the relative formula mass. Now, relative formula mass is just the mass of all of the elements as they are listed in the chemical formula, as it's written in the chemical equation. It can be a molecular substance like water or methane. It could be elements like carbon, magnesium, or iron. Or it could be an ionic substance such as, say, sodium hydroxide or copper sulfate. We just work with the elements as they are written in the formula. And relative formula mass has its own symbol, which is a capital M and a lowercase subscript r. It ends up looking a bit like the English shorthand for the word Mr., but that R should be written as a subscript and not just a lowercase letter. Let's calculate a relative formula mass now. The method is wonderfully simple. Count the atoms in the formula, multiply each one of them by its relative atomic mass, and then add the answers together. Let's begin with carbon dioxide, CO2. Okay, so that's 1 carbon atom and 2 oxygen atoms. So that's 1 times 12 plus 2 times 16, which is 32, for a total of 44. And we've calculated our first relative formula mass. Okay, we'll try water. That's H2O. So that's 2 hydrogens and 1 oxygen. So we've got 2 times 1 for the hydrogens plus 16 for the oxygen, giving us a total of 18. Let's make things a little bit more challenging. This one's glucose, C6H12O6. Well, that's 6 carbons at 12 units each, 12 hydrogens at 1 unit each, and 6 oxygens at 16 units each, giving us a total of 180. And as you can see, once you can count the atoms accurately, the calculation itself is pretty straightforward. Sometimes, however, the chemical formula need to be approached with a little bit of care. For example, here's ethanol. Now, ethanol is often written as C2H5OH, and this actually isn't the molecular formula of ethanol. In fact, it's a condensed structural formula. Its molecular formula would actually be C2H6O. But we can still work with that condensed structural formula. We just have to be careful when we count the atoms. So we've got 2 carbons, we've got 1 oxygen, and we've got 6 hydrogens in total, for a total of 46. The beauty of the formula mass is that it works with calculations with a molecular or structural formulae for molecules and for those with empirical formulae for ionic compounds. If you'd like to know more about those types of formulae and when to use them, then there's a whole video available elsewhere on the channel. But for now, the important point is that not every formula lists the atoms all together, And so it really just comes down to counting them carefully. Let's look at an example formula now that involves a set of brackets. This is calcium hydroxide, CaOH twice. Those brackets are important because everything inside them is multiplied by the subscript on the outside. So we have 1 calcium, but we have 2 oxygens and 2 hydrogens, giving us a total of 40 for the calcium, plus 2 times 16, 32 for the oxygens, and 2 times 1, which is 2, for the hydrogens, which gives us a final total of 74. Whenever you see brackets, remember to expand them in your mind or even on paper before you begin counting. And now it's your turn. Pause the video and calculate the relative formula masses of these 2 compounds, aluminium nitrate and butanol. If those went well, I've put together a worksheet containing some more practice questions. As always, it's completely free and you can download it by following the link in the description below. Today, you've seen how chemists overcame the seemingly impossible problem of measuring the masses of atoms, and why we use the term relative atomic mass. We've seen how such masses can be used to calculate the relative formula mass for every compound you'll meet at GCSE. But this is just the beginning. In the next episode, we'll introduce one of the most important quantities in all of chemistry, the mole. And we'll see how, when combined with formula masses, chemists can predict exactly how much of every substance will be required or produced in a reaction. So, if you haven't already done it, hit that subscribe button now and follow the course to become a qualified chemist. And I'll see you in the next episode. Bye for now.